What I'm going to do now is I'm going to call it example 7. This builds on example 6, which I've done before, and that was the example of AC circuits in a series. Right? So I'm going to use the same numbers. Let's assume there is a source that is given by 1.80 radical 2 sine 2 pi ft, and then the frequency is 10,000 hertz. The resistance is 300 ohms. The inductance is 9.5 millihenries. The capacitance is 0.22 microfarads. And the root mean square voltage, which is the maximum voltage divided by root 2, is 1.80 volts. Okay? So the circuit is now going to be in parallel. So it's going to look like this. So resistance. And then you have the inductance. Then you have the capacitance. So I'm going to want to know what is the equation for the current in each, what's the equation for the total current, and then what's the root mean square current that I will measure in each one, and what's the root mean square current for total, okay? Once I'm able to answer those, then I'm able to analyze pretty much any parallel circuit. So the first thing that you want to do, just like in a series circuit, you want to calculate XL, which is WL, which is the 2 pi times 10,000 times 9.5 millihenries. So you get the same XL as we did in the series circuit, of course. So you're going to get 596.903 ohms. Then you're going to calculate XC, 1 over WC, 1 over 2 pi times 10,000 times 0.22 times 10 to the minus 6, because this one is a micro, right? Now, since we know the XL and the XC and we know the resistance, we can calculate the total impedance in the circuit. So 1 over Z squared, and that one is going to be 596.903 minus 1 over 72.343 squared, right? So we calculate this. 79.3855 ohms. Okay. The next thing to do is to calculate the phase angle phi, right, between the total current and the voltage of the source. So tangent of phi is going to equal 1 over XC minus 1 over XL over 1 over R. Remember that the way it ended up, so then when you subtract that, you get IC minus IL, then you have I total. So we got to do 1 over XC, that comes from here, minus 1 over XL. So what are we going to get here? Because this one goes up there to the numerator. So when you subtract this, you just multiply it by 300. You get 3.64443. Then you take the inverse tangent of that. So now we can actually write down the equation for the current total in the circuit and the current for each one. Okay. So what's the equation for the current in the resistor? The current in the resistor is going to be the voltage of the source, 80 radical 2, divided by the resistance. And basically it is in phase with the voltage of the source. So you're just going to have in the inductor, that's going to be 1.80 radical 2 divided by XL, and then sine of 2 pi 10,000 T, and then it's behind the current in the resistor by pi over 2. The current in the capacitor is going to be 1.80 radical 2 divided by XC, 72.343 sine of 2 pi 10,000 T plus pi over 2. And now we can write down the equation for the total current. The equation for the total current is equal to, now it's going to be 1.80 root 2 over the Z value, 79.3855 sine of 2 pi 10,000 T, and then since the phase angle came out positive, it's going to be 1.303. Positive 1.303 rads. Now, if the question asks me, what's an ammeter going to read? If you put the ammeter in series with the resistor, if you put the ammeter in the circuit with the inductor, what's the ammeter going to read? What's the total ammeter going to read? Okay? The ammeter basically reads this value divided by root 2, right? The maximum value over root 2. So 1.80 root 2 divided by root 2, so that basically cancels. So it's just basically 1.80 over 300, right? We total, if I put it next to the source actually, what's the total current in this circuit? So basically it just reads 1.80 divided by 79. You don't need to worry about this part for what the ammeter is reading. So 1.80 divided by 79.3855. So the current total root mean square 0.0267 amps. So basically you can tell that this is a circuit that is dominated by the capacitors, right? Why? The capacitor has the most current, 0.02488. Okay, actually the capacitor has even more current than the total, right? 0.02267. The current in the inductor and the resistor are actually not too big, 0.003, 0.006. Why is that? Because the capacitive reactance of the capacitor is small. It's like 79 ohms. The resistance is 300. Inductive reactance is 596, so it's very, very high. So it's basically dominated by the capacitors. Okay? Okay, now if the problem tells you at a particular point in time, what's the value of the current in each? Okay? And then we put that 1.26 milliseconds into here, right? So we're gonna get sine of 2 pi times 10,000 times 1.26 times 10 to the minus 3. We calculate that. This part gives me negative 0.5877. Then I multiply it by 1.8 times 2 to the power of 0.5 divided by 300. So the current in the resistor comes out to be negative 0.004988 amps. At that instantaneous point in time, right? Now what's the current in the inductor? So take the 1.26 milliseconds, put it into here. The difference is now you're going to subtract minus pi over 2. Minus pi divided by 2. So this part comes out to be 0.809. Then you multiply it by 1.80 times 2 to the power of 0.5 divided by 596.903. And you get the current in the inductor 0.00345 amps. In the capacitor, so you take this one and then you add pi over 2. Plus pi over 2. And now this one comes out to be negative 0.809. I multiply it by this value, 1.80 times 2 to the power of 0.5 divided by 72.343. So you get negative 0.02847 amps. Okay? Okay, now what's left to do is put the 0.26 over here and then calculate the total current. So I total. This time, instead of putting pi over 2, you're putting this phase angle, 1.303. 1.303. You take the sine of that, and then this one gives you negative 0.9357. You multiply it by 1.80 times 2 to the power of 0.5 divided by 79.3855. 0.55. And you get the total current negative 0.03 amps. And then after that, it's pretty much a bunch of zeros, 0, 0, 0, 0 amps. Okay, let's see what will happen if I add the current in the resistance, the current in the inductance, the current in the capacitance, their instantaneous values. If I add them, will I get the total current in the circuit? Minus 0.02847. And I actually get, when you add these three, you actually get negative 0.03 and with a bunch of 0. And it is actually equal to negative 0.03 amps. Okay, so that's a good happy face. Remember, when you add the instantaneous values of the currents in a parallel circuit or in a series circuit, the instantaneous values of the voltages, you should get the instantaneous value of the source. Okay, in this case, when you add the instantaneous values of each particular current, you should get the instantaneous value of the total current in the circuit. Okay, so I hope this illustrates for you how to approach a circuit where all three elements are in parallel. Okay, thank you very much.